Hey, Math 135, what's up? In this video, we're going to be looking at some additional probability problems from section 7.2 and 7.3. We're going to begin with some card problems. We haven't talked about cards in class yet. Cards are very similar to the finite tiles in that there are a lot of ways to partition. We're using the cards as a selection set. There are many different ways to partition this selection set. For one, there are suits. We have, if you're not familiar with the standard deck of 52 playing cards, we have some spades, some hearts, some diamonds, and some clubs. Diamond and clubs. So those are the suits. You can also see that there are red cards and black cards is another way to partition this selection set. The numbered cards are called pip cards, and they're also referred to as the rank. So the ace is a rank, and all of the cards that have, I guess, the shapes that are on those cards are called pips. So all of those cards are called pip cards, whereas the cards with people on them are called face cards. So again, these are the pip, and these are the face. Is there any other way to partition these? There probably is. We'll come across other ways to partition this set, the playing cards, and we'll talk about it as we need to. All right, so in this first question, we're going to be using, I guess you could think about it as empirical probability, but it's really not, or relative frequency, but we're really using the probability of an event is the number of ways for the event to happen divided by the number of things in the sample space. Now we're just picking one card at random. I guess the thing here that says at random, that's what allows us to assume that this is a uniform sample space. I guess we should have established that before we use this basic probability formula. So when we say that we're picking a card at random, that is I guess that's the signifier that, hey, this is a uniform sample space. That again allows us to use this basic probability formula. All right, so if we want to know, I guess we're going to call the event in part A, we're going to just call it event A. We're not doing the number of things in A yet. We're doing the probability of event A. The probability of event A using our basic probability formula is the number of ways to pick a heart divided by the number of things in our sample space. There's 52 cards. So there's just 52 things in our sample space this time. Let's see. The number of hearts, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 hearts. So 13 divided by 52. Or if you wanted to reduce that fraction, that would be 1/4. What's the probability that we pick a pip card? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 pip cards in each suit and 4 suits. So the probability that we pick a pip card would be the number of pip cards divided by 52, which is 40 divided by 52. The probability that it's not a black face card, we just have to count probability of our event here in C. Probability that it's not a black face card. We could count all of the not black face cards, but it'd be easier just to count, I guess here, hey, let's see. We could do 1 minus the probability of C complement. Let's go ahead and use that complement formula. What's the probability that I do pick a black face card? The complement is pick a black face card. So let's see, a black face card, there's 3 clubs that are face cards, and 3 spades that are face cards. So there's six black face cards. Again, that's what we're counting, or we're finding the probability here. 6 black face cards. And that would leave us with 46 over 52. Then D, what's the probability of a 9 or an ace? We could say, hey, our event here, D, is equal to the event D1 union the event D2, where D1 is the set of 9s. The set of outcomes where we choose a 9, and D2 is the event that we pick an ace. And those are mutually exclusive. Those 2 events are mutually exclusive. So, since those events are mutually exclusive, when I do D1 union D2, that would be the probability of D1 plus the probability of D2. Again, we get to use the easy version of the addition formula because those are mutually exclusive events. D1, there's 4 9s. And D2, there's 4 aces. So that probability is also 4 over 52. Again, I guess I wasn't explicit about it, but we're using this basic probability formula to get the job done here, just counting the number of 9s, counting the number of aces. And this ends up being 8 over 52. Okay, so those are some card problems. The card problems get a lot more interesting when you're picking 3 or 4 or 5 cards. But there's just a nice warm-up to some playing cards. All right, moving on to number 2. In a survey of 3,019 guests, the following question was asked: what is the first thing you do after checking into a hotel room? They give the results of the survey. So this definitely is an empirical probability problem. What is the probability that a person selected at random would, as a first activity, plug in rechargeable electronics? Well, the relative frequency of that, I guess in order to find the relative frequency, we have to know the total number of guests. Hey, they told us the total number of guests. We don't have to do any adding. All right, so whatever this is, it's going to be a fraction over 3,019. The number who plug in rechargeable electronics is 70. Well, that was easy enough. Turn on the TV or unpack. The relative frequency of the people who do that, well, there's 745 who turn on the TV. I guess the frequency of people who turn on the TV or unpack, there's 632 who unpack. The relative frequency, so the numerator is the frequency. When I make it a ratio, it gives me the relative frequency. All right, let's see, 745 plus 632 gives me 1377 over 3019. Now, if they wanted a decimal, I'm not sure exactly what the homework wants here, but if they wanted a decimal, rounded to 3 or 4 decimal places, rounded to 4 decimal places, this would be about 0.4561. Or if I wanted to round it to 3, it'd just be 0.456. All right, so that was a fairly straightforward empirical probability problem. In number 3, we have E and F are 2 events of an experiment with a sample space S. If we have the probability of E and the probability of F and the probability of their intersection, let's compute the following values. The probability of E intersect F would be the probability. There's a formula for that, the addition formula, the general addition formula. We don't know anything about whether or not E and F are mutually exclusive, so we got to say it's the probability of E plus the probability of F minus the probability of their intersection. Actually, the fact that the probability of their intersection is non-zero tells us that they're not mutually exclusive. All right, so that'll be, let's see, 0.5 plus 0.3 minus 0.1, which should give you, I'm jumping ahead, minus 0.1 is 0.7. All right, the probability of E complement, that is going to be, there's a complement formula, or the probability of E complement will be 1 minus the probability of E. The probability of E was given to us, 1 minus 0.5 will be 0.5. The probability of F complement, again, we have a complement formula. The probability, 1 minus the probability of F, and we have the probability of F. It was given to us in the problem. 1 minus 0.3 will be 0.7. And then finally, the probability of E complement intersect F. There is a formula that might work. It would look something along the lines of the probability of E complement plus the probability of F minus the probability of their union. And I've got the probability of E complement and the probability of F, but I think finding the probability of their union, which we don't have, is just as hard of a problem as finding the probability of their intersection. So the formula is not going to do the job for us. We need to make a Venn diagram to finish this guy off. And I think we can make reasonably short work of this Venn diagram. It's just got two sets, E and F. We were given the intersection to start off with was 0.1. We were also given the probability of E is 0.5. We've already got 0.1, and so that leaves 0.4 for the other part of E. The probability of F was 0.3. We already have 0.1 in the football part of F, which leaves 0.2 in the other part of F. And then, since the probability of the entire sample space is always 1, we've got 0.4, 0.5, 0.7. We've got 0.7 inside the bubbles, which leaves 0.3 outside the bubbles. Again, 1 minus 0.7. 0.7 is what we've already have inside the bubbles. 1 minus 0.7 is 0.3 on the outside. And then if I want to know E complement intersect F. All right, the part of E complement that's outside of E that is also and a part of F. So that would be that stuff right there. Okay, so we didn't use the formula for that. We found that using a Venn diagram to be 0.2. Finally, number 4. Is it finally number 4? Okay, we got number 4. A survey of 200 employees of a company regarding their 401k investments. The following data were obtained. 130 had investment in stock funds. 101 had investments in bond funds. 55 had investments in money market funds. 49 had investments in stocks and bonds. 33 had stocks and money market. 34 had bonds and money market, and 22 had all three. So this is looking like one of our big 3-set Venn diagram guys. All right, so let's try to maybe identify some steps. We got stocks. We got stocks. The number of people who own stocks. Yes, that's not our sample space. Yikes. Ooh, there's a problem. That's a problem. Let's just call it T then, since T is the second number of stocks. Let's call it T. Number of people that own stocks will be 130. They told us that the size of our sample space is 200. For bonds, I guess we can call that B. Number of people who own bonds is 101. Number of people own money market is 55. And so on and so forth. I don't want to beat this dead horse. All right, so let's get ourselves a nice 3-set Venn diagram going here, and then we can answer the probability questions that they ask. I might zoom out just a little bit so I don't have to cut off everything. and still have enough space down here. All right, so nice big 3-set Venn diagram. I don't know about you all. I'm getting real sick of these big 3-set Venn diagrams. They're just so boring. Super tedious. But not all that bad. I mean, once you've done one, they all work out to be the same. All right, so we got our 3 sets, T, stocks, bonds, and money market. Starting in the middle, 22 had all 3. For the stocks and bonds football, let's see, there were 49 that had stocks and bonds. We've already got 22. If I do 49 minus 22, that leaves 27. 27. For the bonds and money market football, let's see. Bond and money market, there were 34 who had bond funds and money market funds. We've already got 22. If I do 34 minus 22, that leaves 12 in that part of the football. And then finally, stocks and money market. Remember, we're using T for the people who own stocks. Stocks and money market would be this football. 33 total. We've already got 22, which leaves 11 out there. All right, so we got all the intersections taken care of. Then finally, we can go, let's see, 55 had money markets. We've got 11 plus 22 plus 12 is 33 plus 12 is 45. We got 45 counted. There were 55 total, which leaves 10 people who just had money market funds. For the bonds, there were 101 total. We have 27 plus 22 plus 12 already counted. 27 plus 22, 49. 61, we've counted 61. There were 101 total in the bubble, in the bond bubble. And so that leaves 40 people who just have bonds. Again, that's the 101 total bonds minus the 61 that we'd already counted in other parts of the bond bubble. And then finally, we have 130 who have stocks. We've already counted 11 plus 22 plus 27 is 33 plus 27 is 60. We've counted 60 people already. Again, these 11, 22, and 27 inside the stock bubble here. There's 130 total. 130 minus 60 leaves us 70 people who just have stocks. All right, one last thing to do here. There's 200. There are 200 employees. When we count up all the ones that we've counted, 70 plus 27 plus 40 plus 11 plus 22 plus 12 plus 10. Let's see, we've counted 192 employees so far inside our Venn diagram, which leaves 8 that don't have any investments. Okay, so we got our Venn diagram. This is a Venn diagram with counts. We had a Venn diagram earlier that had some probabilities. Try not to let the fact that there are some probability Venn diagrams and some count Venn diagrams, don't let that be a confusing thing for you. All right, in part A, what is the probability that an employee of the company chosen at random had investments in exactly 2 kinds of investment funds? Exactly. So the two kinds, we have stocks and bonds, but not money market. We have bonds and money market, but not stocks. And we've got stocks and money market, but not bonds. So the frequency of the people who have exactly 2 kinds of investments would be 27 plus 11 plus 12. See, 38 plus 12 is 50. And then the relative frequency would be out of the 200 employees. So we'll call that 0.25. In B, what is the probability that an employee of the company chosen at random, again, we're choosing them at random. That's why we get to just count. Just use the basic probability formula. the number who fit the description by the total, divided by the total. So had investments in exactly one kind of investment fund. Well, that's the 70 who just had stocks, plus the 40 who just had bonds, plus the 10 who just had money market. It looks like there's 120 people who fit that description. So I guess, let's see, the probability of the event in B would be the number of people who satisfy that description divided by the total number. And we just said that there were 120 people out of 200 total. So that would be 0.60 if you wanted to write it as a decimal. And then finally in part C, what is the probability that an employee of the company chosen at random had no investment in any of the 3 types of funds? That's these 8 that we identified on the out one. So again, we're asking for the probability. One of the challenges this semester is keeping track of when are they asking me to count versus when are they asking me to give a probability. Make sure you're reading all the instructions. So again, I'm going to write this out explicitly. That probability of that event in part C would be the number of people who satisfy the description in C divided by the number of employees total. That would be 8 divided by 200, or 0.04 as a decimal. All right, that'll do it for this supplement. If you have any questions about any of these problems or any of the other problems on your homework, please send me a message either in Ivy Learn or using the Ask Your Teacher feature of WebAssign.